Okay, can you listen now?
Sì, a posto, grazie.
So, I don't need it. Okay. So,
You can go ahead.
oh, I go ahead. Okay. So, yeah. So if you want to, so if you complete things with the real numbers, then things exist. Let's say like maximum. I mean, there's no question whether it's rational or not. So things start existing if you complete it. And oh no, it's not quite. Ah.
Okay, now.
Okay. So, okay, on a bit higher level maybe, but still, there are. I would like to argue that maybe it needs to be some things in Banach spaces which are complete, right? But needs extra completion with metric things. So there are a few examples here. It's not a complete list. It's just some examples that I more or less by random encountered. And that's that in mean ergodic theorem, which I will explain in a second, where the counterexample comes. And then there's the famous invariant subspace problem. Okay, that's not known in Hilbert space, but it's a counterexample in L1. And then there are maps, isometries even on weakly convex, the weakly compact convex set that you might expect to have fixed point, but don't have fixed point. And then here's another statement that it's not valid in general, that well, for matrices it's valid. Then this matrix, if you iterate it and apply it on a vector, then that thing usually goes to the largest eigenvalue, absolute value, except if this vector lives in a other type of subspace. But this exists. But for operators in infinite dimension, this may not exist, this limit. But let me, so let's go to, I try to explain a bit the mean ergodic theorem that's usually attributed to von Neumann from 1931. So that comes from dynamical systems of statistical physics. So say X is like a state of a dynamical system, and you apply, and U is the dynamical system that you keep running, and then you take the sum of you measure this system if you want, and take the average, and you hope that this should converge. And usually it should converge to a time. This is the time average to a space average. But if you generalize it to just an operator version, so he worked in L2 because he used his spectral theory to prove this. We'll come back to this later. But if you take just L1, the sequence space, and take this vector, for example, 1, 0, 0, and U be the right shift, so 1 goes to the next place, then this sum here will just fill in 1, 1, 1, 1, 1, 1, n times, and you divide by n's. So the norm will still be 1, but this doesn't converge anything in L1. No weak convergence, no subsequence. It just doesn't converge. This has norm 1, but when you divide by n, coordinates goes to 0. So, and there are many other in L infinity, other counterexamples. So it doesn't hold. But we will see later with metric ideas. This is a very simple idea, right? It's a very simple operator, simple space, natural things, that how it converges in a natural way without any problems. So it becomes, instead of being a counterexample, everything here, except this famous unknown problem, but everything becomes examples of in the metric point of view. Okay, so we'll come back to that point later, the last point. Now, instead, I remind a little review of the first point, that metrics appear in many places. Okay, so first, what do I mean by, okay, metric space is a set with a distance function, satisfying positivity and triangle inequality. And I would consider, so if we think of categorical language, the morphism being non-expansive maps. So that's maps that don't expand distances. So it could be an isometry, or it could be a strict contraction, or something semi-contraction. And isomorphisms are isometries. Okay, so that's kind of say, category, if you want, of metric spaces and these type of maps. And okay, now metric geometry more generally has developed very strongly and become active and useful in many settings. So I cannot review those. Instead, I'm limiting myself to the context that I'm considering here, which is non-expanding map, which in complex analysis, you know well from the beginning from the Schwarzschild lemma and other people's work, say with the Kobayashi method, that holomorphic maps are always non-expansive. Okay, the metric may be zero also, but okay. So here, of course, we have subjects which starts out with a metric. Okay, they are important, Riemannian geometry and Banach spaces. Okay, so we have metrics appearing a priori from the beginning. But then there are, as I already mentioned one or two times, in complex analysis, start this great Schwarzschild lemma that says that every holomorphic self-map of the unit disk cannot expand Poincare distances. And there are generalization that goes quite far. And the Bergman metric is another. But then this more for biholomorphism, being isometries. Then there are metrics, and I think the why metrics appear so maybe it has to do something with positivity. So if you take the positive convex cone, so it generalizes to convex cones, but if you take just a positive quadrant in a finite dimensional vector space, you can put this is half of a metric. Then you can symmetrize it in Hilbert's way or Thomson way. But here's a half a way. You just take, you have two vectors, x and y, which have only positive coordinates. And you can measure them strictly positive. And you take the supremum where they differ the most and take the logarithm. And so looks a bit like an operator norm, except it's logarithm. And so, for example, here in Rome, so one application to Hilbert metric appeared in Liverani's work on decay of correlations. But there are also many other applications, say in game theory and other types of applied math. And I, with a collaborator Benny Avelin, we consider some metrics of this type for deep learning instead of deep neural networks, which fits very well. Another source coming from generalization of the Poincare disk. So this also, it's a generalization of the Poincare disk, in fact. And here's another one. If you have invertible linear maps or mapping class group diffeomorphism, so they act as written here, as in one way on the basic space, like a linear on the vector space or diffeomorphism of a manifold, but you can lift it to a higher level. Now acting on a space of either positive inner products or a space of metrics, a bit more crazy space, and so it induces a natural action there, and there we have a metric. So the first example is exactly the upper half plane, and the 2x2 matrices I said. Well, so 2x2 act on R2, but it also acts on the upper half plane, or this, which can be viewed as the space of positive inner products in R2. Yeah, there was something else I want to say, but I forget now. And then in group theory, there's word metric and Cayley graphs. You also have many actions. So there are quite many actions so by isometry or even non-expansive in math. Okay, now to the second point, the metric tools that I would like to discuss. And so first, we consider the analog of linear function. So in linear algebra or in functional analysis, we have lines, of course. These are maps, morphisms, if I use this language, from R to E, or from E to R. In E to R, that's the linear functionals. And in a topological vector space, you want them to be continuous. And in a Banach space, you want them to have a bounded norm or finite norm. So for metric spaces, well known is geodesics to replace lines. That's the good replacement. It's the shortest path between 2 points. But One would like to say also so these are isometric embeddings of R to X. So you can look at map from X to R, but being isometry is too restrictive since, yeah, for not easy to see. But but we are looking in our category, namely non-expansive maps, and so we are looking and that's also quite many. So I will define exactly which one we suggest to take. And my name for this is metric functionals. There's a name that you would know, but I've changed the name. But okay, so let's try to define this. And if you object to the name functionals, actually in Banach's book, he called maps like this for functionals. I mean, origin is because this used to be a function space of function problem, and functional was something like an integral. So it's a function on functions. But anyway, so we take a metric space X, we fix a base point that will not depend much on this, or basically nothing essential, and we embed X into the space of functions on X. So what is the most canonical way to associate to any point X function is, of course, the distance to X. Now we normalize it so that at origin they are 0, just like, say, linear function are 0 at origin. With this base point. Now if we now we are embedded here, so it's common in topology into a function space. And if we take the product topology, or what means topology of pointwise convergence, now this is compact by Tykhonov or Asselas-Scully argument, because this is one Lipschitz map. And so we have obtained something compact. Even though X was anything, we have something compact. Of course, this can be a bit crazy, but okay, that's what we have. And I call those elements for metric functionals. And of course, in your head, probably you think of Horo functions and Busemann functions. I will come to that soon. And I call this the metric compactification. That's also a term used by Riefel in operator algebra. And it's similar to one of Gromov, but he picked another topology, namely uniform convergence on bounded sets, which had other features that was maybe more interesting to him at the time. So the most canonical, a little bit like the canonical type of or standard linear functional is you take a vector and take the scalar product against this vector. That's in Hilbert space, that's all there is. And so a bit similar is that here we take, instead of a vector, we take a geodesic ray, and then Busemann observed that this limit is bounded by triangular inequality. It's also monotone by triangular inequality, so it exists in any metric space. So that gives a function, and if you saw here, that's exactly when we take this closure. So we're taking limits of all this. When X goes, we look at these functions of this variable. When X goes to infinity, so this space is all these functions and all their limits. And here is one typical type of limit. You go along a geodesic ray. And indeed, and they call it Busemann function, this is quite standard. And if X is a Hilbert space, and you take a vector norm 1, and you go along that line and do this limit, to calculate this limit, you recover the inner product against V. Okay, up to a sign. That's the normal sign for Busemann. And so in this schematic of things, so metric function is everything. And then Busemann was these particularly nice ones. And then Horo functions is, I call, in order to distinguish the terms, with the topology that Gromov picked. And so they are a bit, require more to converge. So you have more metric functions than Horo functions. If the space is proper, so I mean locally compact and geodesic, they coincide. So for some cases, of course, we can keep talking about Horo function. But in general spaces, maybe I suggest this term just to think of it as something fundamental and also in analogy with linear functions. Okay, so maybe some examples. here I recall the definition. And so let's study one of the most easiest metric spaces, which are not yet compact. So that's just a real line with the usual distance. And so we take this 0 as the base point. And now we are wondering what happens here. So these functions are concrete enough, but we are asking ourselves, what are the limits? We try to identify the limits. So we are sending n to infinity. And we look at that function is this function. Here I replaced the distance by this absolute value, and we have y as the point. And now if n is bigger, then you understand the sign of this. You can remove the absolute values, and you end up, so n cancels, and you get it with a finite value. And so when n tends to infinity, that's the function you get. And that's, you see, that's coherent with what I said with the Hilbert space, since this is just scalar product with a vector 1 or minus 1. And so you get 2-point compactification of the real line in this manner by adding these two functions. So that's the simplest example. And then there are more in non-positive curvature. It's been the Busemann function has been a tool both in non-positive curvature and non-negative curvature. But here, I'm not the only one, but I'd like to advertise use for in any type of without curvature condition. So here the Poincare disk again, and here we have a geodesic, and it goes to that boundary point of the circle, and so here's gamma, and so this is our Busemann function, because this is a kind of reflexive space. Every Hor function or metric function comes from a geodesic ray, and the circles here are the level sets of this function, which are called then Hor disks or Hor balls or Hor circles, cycles. So you get this. I don't go through the proof of this. Now maybe leave this also aside. This one is a bit easier. So it's z squared, so with a metric of L1, so the Manhattan metric that the graph indicates here. Then what you get is just, actually you can almost see that from R, you had these 2 points, except we made it z, but you have plus infinity, minus infinity, but then you have the product, and because L1 is, that product doesn't mix the 2 coordinates, I mean they are additive, so then the analysis we just carried out here, you do this component-wise, and you get then a compactification of z squared in this fashion. You just add plus and minus infinity in each coordinate. And here, so there are many more examples nowadays, in the last few years. And so, for example, for Gromov hyperbolic cases, it was known that this metric, the Hor function, could be several for each Gromov boundary. So if you don't know Gromov hyperbolic spaces, maybe it's okay for now. But so there's a recent paper by Rossi, Fiacchi, Gonta, and Guerini where they show that bounded strongly pseudoconvex domains with the Kobayashi metric, or this with Kobayashi metric, that these two compactifications coincide, and it's also coincide with the one you see extrinsically, and the consequence about the small and large Hor space coincide. So this is quite nice work. Furthering, they do other things, but in particular, an example of how to understand this metric compactification. And here is an infinite dimensional example. So we're taking a Hilbert space, the real Hilbert space, infinite dimension, and now we are compactifying this Hilbert space. So we're used to that the closed unit ball is weakly compact, but here we're doing something. It's related, but it's a bit different. We compactify the whole space, and it's parameterized by a radius and by direction. And the direction here you have the unit ball, and indeed the points converge in this compactification. They weakly converge in this to a vector v and stabilize, converge in this radius. And if they go to infinity, and so you have this type of function with these are a bit exotic ones. And here are the ones that when you tend to infinity, you see again our friends, the linear functionals. But here with vector taken here. And there are other results more recent for especially LP spaces by Cormac Walsh or Armando Gutierrez. So it's starting to be understood well. So more general version of this thing. Okay, maybe this, I don't know if doesn't need to speak about. But here, Gutierrez noticed one nice thing. For the sequence space little L1, the function that's identically 0 does not appear among the metric function. Of course, it's a linear function. And it's a bit sometimes vexing linear functions is sometimes, you take weak limits, say, and then suddenly you just get 0, even if the vectors were not they had not norm tending to 0, but you can get some kind of disappearing limit. But that doesn't happen in this space. Okay, so let's continue our metric analogs. Now we discussed one notion, the notion of Busemann function, Horner function, or metric functional to be kind of the replacement of linear function. And now I will discuss kind of some of the theorems of functional analysis in this metric type of way. So we saw this weak topology that is by mapping your metric space inside this function space with the pointwise convergence, we have some kind of weak topology now, and with the compactness properties. So that's something good in function analysis. That's one of the use of linear functions there to have this compactness at hand. So if you have some solution to a differential equation that needs to exist, and first maybe you can only get the weak solution and you promote it and so on. So that's one of the uses of functions. And there's an analog with Hahn-Banach. So just if you have any subspace, okay, maybe contain the same base point. They share the same base point, never metric function standard. And those statements are not true for Horner function. So these are the type of topology. Okay, now to analyzing operator theory. So here's the linear notions that you probably studied a long time ago. And here, the metric analysis. So you have the operator norm, right? So here E is a norm vector space, A is a linear map, and here's the operator norm. And then there's also the spectral radius. This turns out to be also the soup of the spectrum, but that limit exists by submultiplicative observation. And it's smaller or equal to the norm. And if the A is a nice operator, like a self-adjoint operator or normal operator, they are equal. Okay, what about metric spaces and a non-expansive map, F? One defines the minimal displacement. So looking at the vector that's moved the least by F. So in particular, if there is a fixed point, then that number will be 0. And I think it's not totally clear, but it seems to be a bit an analogy of the norm. And then there's the translation number that's a bit more clear, an analog of this spectral radius. It's when you iterate your map, the operator, or your map here, in fact, and you look at the distance when you divide by n, that converges by the same reason as here, except that there's a log. Here is sub-additive, here it's sub-multiplicative. But it becomes, of course, sub-additive when you take a log. Now, this number always exists, and it's also easy to see that it's at most the displacement function. So here I started iterating this point. And iterating a function is, it's a dynamical topic of dynamical system, but also it's a way of studying the F. So even if you not care about dynamical system, you want to maybe understand your self-map F, and one way is to iterate. And so you take this average, okay, so those are classical notions, more or less, especially this one, maybe even most used in hyperbolic geometry to classify isometry. but they make sense for any holomorphic self-map. And so one can ask questions. I had a discussion with Andrew Seymour about this some years ago. We could ask when there are the equality. So I recall that. So when, in other words, when is this equal to this? And there are some answers for isometries and some metric spaces in different cases. Maybe I don't go into, but there are some answers emerging, but it's not the full picture. And I think we talked this morning. We think that this is interesting also in the complex setting, even though they're less classical of interest. Okay, and here's I call it the metric spectral statement. That okay, it's a bit long time ago, but there's a complement by Gobert-Vigéral in case X has a bicommon, which is some kind of weak non-positive curvature. You can upgrade this. But anyway, this is any non-expanding map of any metric space, locally compact or not. Then there exists the metric functional such which is kind of traps the orbit inside its horoball in this fashion with the maximum rate possible, because that's the rate with which the orbit escapes. Of course, this number could be 0, but then this is a valid statement, and this holds for every k. So it's not allowed to sidestep outside this horoball. And so this is the statement, and what's the refinement of this is this holds for every x. So the horoball is an invariant set in the sense of dynamical system mapped inside. And so now, why do I call it this? Maybe you because some of you are familiar with that. This is Wolff-Duanchois theorem, but it's because it's more, to me, it generalizes other results too that I will come to. So I kind of suggest this name because I'm trying to get this argue for an analogy. But we'll come back to this. Maybe first prove how do you get this H? So given this very general setting, how do we get this? And the proof is as follows. So let AN be the distance from the starting point to the nth point. And that's a subadditive sequence because of triangle inequality for D and because F is a non-expansive map. And therefore there is this rate of escape, or which I call, I forgot what I call it, the translation length. The analog of the spectral rate exists, but now for this I changed letter A. Because now I'll use only subadditivity, not, yeah, okay. So that's the time average of this sequence. So you have a small error that tends to 0. I mean, measured when divided by n. Now fix some numbers going to positive numbers going to 0. Yeah. And let B I n. So I is this I, n is this n. That is. Now A is the rate of escape. A times n is how this escaped. So this means that these numbers are unbounded. And when you have unbounded, you can take a record time. So that means a time which is larger, or sorry, a time for which B is larger than all the previous. So I could have taken this instead. I could not have taken this, but this point is good, this point. And I do this for each I. And now I measure the deviation, the defect of being an additive sequence. If it's an additive sequence, it's kind of things are lined up. And so I measure this defect to being an additive sequence rather than subadditive. So subadditive just means that this is a negative number. So I could have had an inequality again. But here we're looking for the bound in the other direction. So I rewrite it in terms of the B, and then I have to add those things in order for doing this. And here I write AK coming from this formula. Now the point of this is that the B, and that was a record time. So then that one is for sure bigger than this. So by estimating from or making something smaller, I can remove this because I know this is positive. Because this was a record time, this is bigger than some of the stuff. And then this cancels, and then, but I get this kappa k, That cancels, this cancels, and I get this. So I get this small number times k. So the defect is small up to scale k for any k in between ni, n1 and ni. And that makes us possible to put these together. If you go now n1, you can apply n2, that this triangle is almost additive, the distance. So this is a bit schematic picture, but the intuition maybe is that they are kind of lined up at this special. So this special time, record time, is when your orbit is definitely away from starting point. And when you apply this, you kind of get a direction, and this metric functional is like a direction. And so we take a weak limit point of this special orbit point, and thanks to the weak compactness, So, and that weak limit would be our h, and then it will satisfy the properties. Maybe it's not totally clear, but I guess it has to suffice for the moment. And so now comes to the special cases of this. So it's very special cases, since it's for any metric space. But so I basically take special cases when they're famous names, it seems. So yeah, here you can prove it for matrices that you have this type of exponents. But the first in history was this Wunsch-Dolz-Schwab independent work in 1926, I think, about holomorphic maps that either is fixed point. Okay, so this fixed point is not part of the previous result. That depends if the space, I mean, it was any metric space, so there is no way of getting a fixed point in general. I mean, you could apply it to a circle, and you just rotate a fixed rotation around the circle, apply the previous, I mean, this applies to x could be a circle and f a rotation, and this still holds, but it's a bit vacuous state, almost vacuous, but of course trivial state. But of course there's no fixed point, even though things are stay bounded. Okay, but it also implies, when you apply this to, I will explain this a bit more later, how it implies this. But if you have U, this is the mean ergodic theorem I talked about, the operator version. So you have a linear operator at norm at most 1, then this converges if this is a Hilbert space. And I'll show how to deduce this later. And there is a Thurston spectral theorem. So given a homeomorphism of a surface, genus G surface to itself, you can look at, you can iterate. So alpha is, I don't formulate it in detail because, yeah, we focus on other things, but alpha is a closed curve on this surface, and you're looking how this curve starts winding around when you apply your homeomorphism, and then look at the length of it. To be precise, it's actually length up to homotopy, and then divide by n. Then you have a statement like this, that there are these exponents. And you see, I want to point out the analogy with here. Here you have a vector, and you have a linear map. Here you have a curve, you have this homeomorphism. Here you have a length, a norm. Here you have some length of this surface, and you prove this. And the way this goes, as I said before, instead of looking at the action on the surface, you lift it to the Teichmüller space. So this is like a space of metrics on the surface, where you have an isometric action. In fact, in this case, I use Thurston's asymmetric metric, which is a bit similar to the Hilbert-Thomson metric we talked about before. I could have used the Teichmüller metric, then, which is a Kobayashi metric, and then you get similar result, but for the extremal length and not the hyperbolic length. And Cormac Walsh showed how to identify the Bohr functions in this Teichmüller space, and using that one can deduce this. And Horbes showed how to get more exponent and not just the top one that I couldn't do. But so there's a metric approach to this thing. The Thurston's was using foliation theory. But you see the analogy, and you see that, okay, each case needs some more ingredients. It's not direct consequence of the, but I think the main mechanism is the one of the, what I call metric spectral theorem. And another advantage of this metric point of view is that it extends to a random version. The proof of the subadditivity becomes more difficult. Well, here was another proof using isometry and its action on the metric functionals. But here is Sebastian Gusel. He saw how to, it's a complicated subadditive argument that was an ingredient needed. And then there's the same proof as I outlined before, to show that for any random iteration of non-expansive map, so now I don't take one fixed and iterate, but instead maybe I take 6 of my favorite maps, could be holomorphic maps over, say, unit disk, and I throw a dice and I apply it each time I see corresponding number. And I multiply them in this order, that's important. And then again, you have some kind of, either nothing happens, they maybe your maps were just identity maps, then not happen much. That's the case when this limit is 0. In the other case, there is this directional behavior. I mean, so that depends on how to analyze your metric space of interest. What are these metric functionals? But then there is this non-commutative ergodic theorem concept. And okay, here's a picture, and so yeah, it applies to holomorphic maps. So not enough maybe studied in this case. And it kind of answered the question of Furstenberg of getting such a non-commutative. So an extension of the law of large number, but now when your random variables don't commute anymore. And so to my mind, it's a good reply to that question. And for matrices, this was already known. It's a fundamental theorem in smooth dynamics. They call those multiplicative ergodic theorem. Okay, so but maybe go back to the third point is, so this my talking about why we need the metric methods, notions even to formulate the answer of linear problems, so to avoid the counterexample. Of course, to analyze when different things happen is still useful, but as I try to argue, sometimes one wants things to exist, want the maximum to exist. You don't. So that's convenient to have real numbers rather than sequences of rational. Okay, so that's would be to explain the mean ergodic theorem that von Neumann was quite proud of, apparently. And we noticed how it failed in L1. And so let me go back. So I don't have it. Maybe I skip one. So the topic was to try to show that 1 over n times this average, or 1 to the n times this sum converges. And so but if you apply directly the metric spectral theorem to this operator, or this non-expansive map, where U is a linear map with norm at most 1, guaranteeing the contractive property, and then the translation of V, which of course preserves all the distances, and you take the iterates of F, that's exactly this sum. And now the metric spectral statement assures you that there is a metric function H for which this statement holds. And now it's for all n, so it's a bit a priori, as a statement, it's a bit stronger than the mean ergodic theorem, since it's not just 1 over n tends to something, but you have this. And tau, which is can be determined this way. So this is like the infimum displacement, which equals actually this escape rate that we had before. And so how does it imply in Hilbert space? Well, so we are interested in, so I let W, W is the one, is the vector. So we take a linear functional. And okay, either this tau is 0, then it's the kind of end of the story. Then, okay, this average tends to 0 and we are happy. Or there's metric function, and I had a list of what they were in Hilbert space. But the only one that qualifies because of tau is the maximum, is the same rate as the norm of this, and H is kind of yeah, it's the one Lipschitz map. So H must be of the form W unit vector scalar product. So the one we get here is of this sort. And then when you now expand this inner product, you get this, and since that's a norm 1 vector, so that's this tau squared, and this tends to minus tau, you can take out tau, and then this thing, thanks to exactly the statement of the metric spectral, this tends to tau, and the first part by since that's a unit vector, just by that's the just this subadditivity applies this. So you get that this converges to 0, which is exactly the statement that converges to this vector tau, which we have separated. The tau is the length and W is the direction. So it implies this theorem once we know the metric functions. But the point is that this also applies for the counterexamples in the beginning. So the counterexamples, there were several, and I cannot go through all of them, but all of them are a bit of this flavor that they stop to be counterexample once you look at it metrically. And so the counterexample in the beginning, which was the sequence space L1, then you have the right shift, and you started maybe with just vector 1, and then you shifted this 1 and took the sum. So your vector became 1, 1, 1, 1. So it's as if it went to 1, 1, 1, 1, 1, but that's not in L1. But you see here the H has this 1, 1 here, and when you apply it to this thing, then whenever this is most of the time this is 0, so then this becomes 1, and 1 minus 1 is 0. So H from the beginning is kind of 0, and then you start filling in the ones when you shift it and take the sum, and you see that every time you put the 1 there, 1 minus 1 is 0, you pick up a minus 1, which is like what this says that you should do. And so the sequence converges to H, and H has this property that you see exactly what happens. You see, of course, it's a very simple example to analyze this shift, but here you also it fits into the picture. And I think that was it. So thanks for your attention.
Thank you very much, Anders. So are there questions from here or from home? Okay, I do have one which so you can construct a metric functional maybe even with not in every space, but in like in the disk with the Poincare metric or maybe strongly convex domain.
Yeah.
You keep a geodesic line.
Yeah.
And then you can keep a point and look to the closest one. So yeah. This gives a kind of projection which is also a contraction.
Ah, yeah.
So. And this, if I understand correctly, this means that you can find a function which gives this this kind of metric functional.
Yeah, there will be in finite dimension there will be Horo functions. Yeah.
Okay.
Yeah. And I forgot to say that they go by visual. They use kind of Beardon's method to prove. And another thing I wanted to say was that yeah, okay. Yeah, there are other applications where you don't have them, but okay, it gets a bit too far. But I came to think about it.
Okay.
The prediction.
Other questions? Okay, so if not, I thank Anders again. Okay.